Hi, it's Andre again with another update on the MicroPET. Some good news and some bad news, so stay tuned. So what I've done here is I have created a ROM simulator, little board where you can simulate the data output of RAM or ROM. Just should not write to it, and then the video is running, and you can see now this is the video output. And if you look closer, it's EA, which is a knob for the 6502, and that's what I'm going to try next. That is using that as a ROM simulator and running the CPU on it. So as I've just explained, I wanted to use this knob generator together with the CPU, and I actually did, but you should actually never ever try to do that, because of course this is a 65816 from Western Design Center, and it uses the database to write out the bank address in the first half of the cycle. So this CPU in the first half of the cycle is driving the data bus against this knob generator. So I just hope I haven't broken the CPU. I will have to test it again. I was a bit careful and cautious and put in a 100 ohm resistor, so I'm not shorting the lines with that knob generator, so I only hope that the CPU is not broken. What I observed was, though, is that the CPU was actually cycling the address lines, so I could see the address lines wiggling around from A0 to A15, which is what is expected with a knob generator. What I've then done is I had removed the CPU and used this one as a bank generator for the CPLD, and have been looking at the various select signals and the timing and so on, and have been improving on this one. So the next step will actually be, because this is already in that stage, that I will remove that signal generator or knob generator excuse me, and I will put in a ROM that has actual knobs programmed into it, and see what the CPU does. So let's have a look at the architecture of the MicroPET. There are three goals that I wanted to achieve, and I haven't succeeded in yet totally, but those are the goals that I started out with. So it should have a low board area, which is mostly equivalent to a low chip count, so you don't have to solder that much. There should not have been any surface mount device chips, so that you would be able to solder that easily with through-hole parts. And the parts should still be available. So I have been looking at a number of alternatives. For example, this one here, where I had tried to build the system out of multiple programmable parts, like this controller, the mapper, and the video, all separate into these CPLD package chips that you can solder with through-hole sockets, or like even this size chips of the same type. Even I was looking into putting the video shift register outside of the CPLD and so on, but that was all adding to the chip count and to the surface area on the board, and also those parts are already discontinued, so you can still get them, but CPLD sockets are not basically not supported anymore by the producer of those chips. So what I ended up with in the end was this design. which looks rather clean now because basically I've put all the important stuff into the CPLD. I decided to actually take that as an opportunity to build a really nice CPLD, nice system architecture around a single CPLD that controls the RAM in its entirety. So all the accesses to the RAM, either from the video part in the CPLD or from the CPU, have to go through the CPLD, and it controls all the timing. And on the other side, there is the CPU, the ROM, and the I/O on a common bus that you can actually maybe in a future version extend with some kind of pluggable bus system like extension cards or so. So basically, if you look at the CPU, it's a 65816. It sends in the first half of its cycle the bank address to the data bus, which gets read in by the CPLD, which then does the mapping of the address ranges and so on. It also uses a 12 to a 15 from the CPU and translates them into appropriate RAM or even ROM addresses here. And that's basically it. It's really a very simple architecture. And as you can see, I have been getting quite far with it so far. So let's have a look what the current state is. As you can see, the ROM socket and the CPU socket have been populated with the ROM and the CPU chip. And I have been programming the ROM with a knob sled, so basically 4 kilobyte of area just filled with the CPU's no operation instruction, and have been restricting the CPU with using the mapper in the CPLD to just that single 4K block of memory. So what the CPU should do, it should just read those knobs and then just continue cycling the program counter. And that's what we can see next on the oscilloscope. So I have started the machine with the knob sled running, so the CPU is just walking through all the knob operations, and what you can see here now is A15, which is the uppermost address bit, if you don't count the bank, and what you see here is that it has a cycle time of 24.6 milliseconds. How does this result in 24.6 milliseconds? Let's do some calculations. A15 is the uppermost address bit, so of a 16-bit counter basically, because it's just running through all the addresses it can do. So there should be 65,536 cycles, or should they? So we'll have a look. And that's why I'm going to look at A14. What you can see here is, obviously, it has half the cycles because it's just a counter, and A14 has double the frequency of A15. A1 and then A0. So let's have a look at the cycle time of the lowest address bit. Going to the cursor again. So what we see here is 752 nanoseconds. Oh yeah, oh I got it. It's actually 6 cycles, because sometimes even I can get confused, because that is a single memory access. And that takes about 360 nanoseconds. And actually this is not a single memory access. It's actually one execution of the knob operation. Now what you can see, this is the Phi 2 clock, and you can see that we have 3 cycles within one execution of the knob operation. And if I get it right, and this is actually what you can see here, this is the ready signal. So actually it shows that the first cycle is reading the opcode and then doing one cycle nothing. Then the first cycle is reading the opcode, which takes 2 cycles, one with ready, then actually reading it, and then there is another cycle where the CPU does nothing, and then it increases the memory address and goes to the next execution. So what I've learned in the meantime is that using ready on the 816 processor is not that easy. As I mentioned on using the ROM simulator, the processor is sending out the bank address on the first half of the cycle, but it also does so during the ready, if ready is assigned. So if you try to spread one read access from, for example, a slow ROM across 2 cycles, there will be a phase where the clock is low, and the first half of the second cycle, the CPU will still send out the bank address and will push it against the data that is coming out of the ROM in this regard, in this period of time. So what I did, I changed the system to not use ready, but instead to stretch the clock cycle. So what you can see here on the lower on the lower signal is the select signal for the ROM, and on the upper signal you see the Phi 2 clock. So what you can see is that there are short and long cycles on the clock itself to accommodate for the fact that the CPU has to be waiting. It's not ideal, but it has to work that way right now. So let's get to the good news that I mentioned. The CPU is now running and it's executing code from the ROM chip, and it's actually also writing to the RAM chip, as you can see in the next part. So what you see here is a screen output from a small assembler program running in ROM and modifying the screen memory, incrementing every byte in the screen memory over and over and over again. You can see probably the resolution is not good enough for the camera, but you can see the stripes that build the binary numbers on that image, and you can see it counting up. And after that good news, there's also some bad news. So what I have learned is that driving the Phi 2 clock from the CPLD to the 65816 is not fully according to specification, it seems, of the processor. It seems there are some glitches that come up because the clock is not, signal is not good enough and not high enough from a voltage level according to the specifications. Currently I'm running the CPLD in 3.3 volts because that's how it works. It's just 5 volt tolerant on the input, and the processor is running on 5 volts. The reason for this is that all the I/O that is here in the system, that will be here at some point in time, is 5 volt I/O, and also the I/O chips from Western Design Center, the PIA and the VIA, they are also only capable of doing 5 volts when they are run with 5 volts, and they don't allow signals on the data bus and so on that are above that supply voltage. So the CPU has to run at 5 volts as well. So the system was unstable when I first tried it, but I have been finding out the solution that where I can push the Phi2 clock signal through up to 3.3 volts and then leave the rest to the to a pull-up resistor, which is actually from an application note from Xilinx how you should be doing that, and that seems to have improved the quality of the clock signal far enough to make the system stable again. However, what I see is that the voltage level is not fully reached, and also the same problem will potentially appear on the data bus once the CPU starts reading the data from the RAM, which is going through the CPLD. So for me it's unclear what the next steps will be. Several options. First, I'll probably try to save that board by trying to see if I can actually read data from that RAM using that trick, and if that is stable enough. But certainly for a later version of the board there will be some real voltage regulator in between. Then the next option will be probably to change the video timing. So I have been looking into creating VGA timing for the video output, so we can get a black and white VGA output, which is much more common on monitors nowadays than a composite input that this circuitry here is producing. And then also another option is to look at the replacing the ROM with a serial ROM. So this is 8-bit parallel ROM. There are serial ROMs with an SPI interface, and I have to be evaluating if the CPLD has enough resources left to be able to create an SPI interface for that serial ROM, and also, because otherwise there's no ROM, no code that the CPU can execute, how to basically load some code from that serial flash ROM into RAM for the CPU to execute. So those are the 3 options that I'm looking at. Leave your comments below. What do you think I should be going? And thanks for watching, and see you next time.